Come on in, everyone. How are we doing? Anybody have any questions before we get started? Nicholas, can you hear me? You can shake your head. I see your face, so that helps. Looks like Nicholas cannot hear me. No here. Anybody hear me?
Yeah, I can hear you.
Okay, good. Maybe it's just Nicholas that didn't hear me. Okay. And I can hear y'all, so that's good. Oh, I see. Nicholas was there, but his audio was connected. Sorry about that, Nicholas. I was talking to you, asking if you could hear me, but you couldn't. Good deal. Anybody have any questions before we get started?
I got a question.
Good for it, Nick.
I can't access the online test.
That was me. So basically, I was just going to tell you, I just opened it. Remember, I sent an email. Hopefully, you saw it. I sent an email. I want to say it was either late Wednesday or early Thursday, just saying that I decided to give y'all another week to do the test, just because I didn't want to you guys to be rushed, and I didn't get a chance to remind everybody properly and all sorts of stuff. So what I did was I just made it available now. You have until basically Sunday 11:59 p.m. to get your attempts done.
Okay, yeah, I got that email. I thought it was still accessible. You were just extending the deadline for it out. I just kind of misunderstood.
Yeah, I actually completely. What happened was there was a problem when I went to go to launch it, that it wouldn't launch. So I figured it'd take me a little while to get it fixed, and I'd only be able to offer it on the weekend, and that gives some people an advantage. And so I just did it today. So sorry about that. That's all my screw up, everybody. But make sure you get it, write it down on your calendar somewhere. Make sure you take it at least once before Sunday at midnight. I would suggest you take it as soon as you're ready to, as soon as possible. Maybe take the practice test a couple times for test one, and then take it once just to get a grade in there. That way, if you accidentally forget it or something comes up, you won't miss it. Chapter 23 homework for you guys, it should not be due. I'm gonna have to move that back. I forgot that you guys had the Monday off because of Martin Luther King Day. So I'm going to set that date back on chapter 23. Let me write a note about that. 23, we're just starting today, so that it wouldn't be unusual or completely unreasonable for me to have you do the conceptual questions for chapter 23. But I don't think that's appropriate. So I'm going to go ahead and push that back. Anybody else? Cadmium, I know you and we have something to work around. I'm having some difficulties getting that taken care of, but we'll get it. Just keep plugging along on this course as best you can, and I'll make everything else work out. Anyone else? All right, well, let's get started. So chapter 21, we talked about electric fields. Specifically, we started off with the Coulomb force, and then we used the idea of field to get rid of that creepy action at a distance thing that was going on. And basically what we ended up doing was we took the electric field we took the force and divided out of it the electric charge that we thought would be feeling the force. So we left one charge and we looked at that charge as the source of the force that could come from, or the source of the electric field that could cause a force on the other one. And then the other one was the one that would feel it. And basically that was just a difference of taking the force and dividing it by a charge. So we got a neat new relationship that says the electric field is equal to the force divided by the charge. And gave us a unit for the electric field in newtons per coulomb. Today we're going to introduce another quantity, and it's really voltage. What you know of is the stuff that comes from your power lines inside your house and your receptacles and whatnot, which is equivalent to potential energy. In fact, if you look at a lot of electronic technicians manuals and stuff like that, they'll often picture a circuit as you go from the power supply, which might be just a battery. You go from the negative end of the battery uphill to some voltage, say 10 volts, and then you stay at that same height, like, well, I say same height like this, and then you run into a resistor, which might just be a light bulb, and that's like some steps down, and then you go back on the same level to the bottom of the battery. And the reason why they do things like that, showing it in 3 dimensions, is because really it is just, it's a form of potential energy in some sense, okay? The units for the volts are not potential energy, but they're called electric potential. So it's called electric potential. It's also called voltage, but it is related to potential energy. But when you put the word energy on it, it goes back to energy. So we'll show you how to get back and forth between those two. But oddly enough, it's just going to be the same way we got the electric field from the force. We divided by a charge. So the similar thing's going to happen here. We're going to take the potential energy, which remember in the case of gravity was mgh, or in the case of a spring was 1/2 kx squared. If we took and divided out the mass that was experiencing that, then that would be sort of the equivalent of the gravitational potential in the case of mgh. Okay, so in this case, we're doing the electrical potential, or the electric potential, or the voltage. All those are 3 words for this, or 3 phrases for the same thing. And that's just found by taking the potential energy and dividing it by the charge. So let's get started on that. Again, no problem, Shimon. I'm not sure how to pronounce your name. I apologize for whatever I was just saying.
No, you're fine. It's Shimon
Okay.
when you're feeling fancy.
Okay. Well, I'm horrible in names, period. So I always look like the idiot that don't know anything. So I apologize if I ever.
No, you're fine. You're fine. It's no worries.
So anyone have any other questions before we get started? Well, we've only had one, I know, but I want to make sure I give everybody a chance. If you have homework related questions, you can save those to the end. I might not have told you last time. I think you guys got it right. I think I went all the way through the infinite disk using Gauss's law. But in one class, I did it after the class was over. Oh yeah, that was the day class. I remember, because I thought class was ended at 12. I stopped class at 12, and class actually ran into 12:20. So yeah, I'm that dude. All right, well, let me go ahead and switch to my document cam, and we're going to talk about this concept of electric potential, also called electrical potential, also called voltage. Okay, so let's do that. Oops, wrong thing. So we have a quantity that's called the electric potential, and we're going to define it this way. We're going to say that the electric potential at any particular point A is equal to the potential energy at A divided by the charge that's experiencing that potential energy. So in other words, we're going to say there's a potential energy. Remember, potential energy is basically the change in potential energy is equal to the work done on the system. That's a way of looking at it. Therefore, you can think of this as the negative of the work done by the system. And therefore, you get this change in potential energy can mean something electrical if we just think about what I'm going to have to do to a charge to move it from one point to another. So that's really the definition. I think you can automatically see that that's going to mean the units of the volt. So here's those boxes again to remind you that that means units are dimensions. They're going to be joules per Coulomb. Okay. So 1 volt is equal to 1 joule per Coulomb. And what that means is if you have a voltage of 1 volt, you basically could give a 1 Coulomb charge enough potential energy to basically lift the apple from the ground and lift it to the top of a dining room table. That's what a joule is. A joule is that much potential energy. So that should give you some idea roughly what it is. Well, now we know work is normally equal to the integral of F dot dl. Okay. And that's the work done on a system, for instance. And if you wanted to take and say, okay, well, what if I wanted to relate work to potential energy, because that's what I told you how we could always define a potential energy, then I might think about, well, what about the potential energy per unit charge? If I did that, then I might even think about work equals Q times E dot dl. because now I have, instead of the force, we were using the definition of the electric field, which, remember, the electric field was equal to the limit as Q approached zero, almost right infinity there, of the force divided by the charge Q. In other words, we're picturing from F equals K Q over R squared. We're picturing this Q as being the source or the creator of something called the electric field, and then this Q being the thing that's receiving it. But in principle, if the little q is receiving it, the little q can also be a source of electric field. Therefore, it's going to create electric field, and therefore it would alter the electric field. So they're trying to imagine the limit as little q goes to zero. That way, this electric field will be of no concern whatsoever to calculate in this electric field. So that's why that whole limit's in there. In practice, the equation is just basically, you can say F is equal to Q times E. That's it. And it actually is a vector equation. So you can actually use the vectors and get out the magnitude too. So if you know the magnitude of the electric field and the direction, you can just multiply that by the charge with the actual sign, and that will give you the magnitude and direction of the force. So that's something to keep in mind. So now that we've expressed this work as something related to the electric field, all we have to do is say, well, let's take the change in potential energy, which we normally indicate by delta. Remember, delta means change in. And whenever you see that, you always want to think final minus initial. So I'm going to write that is UB minus UA, where B would be the final spot and A would be the initial spot. Well, I think it makes sense to call that the negative of the work done in going from A to B. So remember, if I do work on a system, like if I lift a baby up, okay, I apply a force to the baby. So here's a little fat baby, little fat pudgy legs, little fat belly. Okay, he just got freakishly large. I don't know what happened. Okay, so if I apply a force to the baby, F, in this way, and he moves up a height H this way, okay, what I've done is cause the baby to go from U equals 0 to U equals mgh, right? Where this F is just mg. So by putting work into the system, that caused the change in potential energy. So what that tells you is this is the negative of the work done by the system. So that's why the negative there is there. It's not the work done on the system, it's the work done by the system. Okay. So if I write it that way, then I can say it's equal to the negative of the integral of F dot dl, but F is really just the same thing as E times Q. So I could write it as negative Q times the integral of E dot dl. And then from that, I can say, okay, well, there's this quantity delta V, which is VB minus VA, which is equal to delta U over Q. And that's equal to the negative integral of E dot dl from A to B. That's our definition. Okay. So the change in voltage, which would be VB final minus VA, which is the initial, is equal to delta U over Q, which is equal to the negative integral E dot dl. And this is that line integral I taught you about last semester, those of you who had me last semester, where you've got to choose either DL pointing in the positive coordinate directions and then A and B telling you which direction you're going, which could still be the positive coordinate directions, that'll be fine. Or you've got to use the DL to point in the direction that you're going and doing the integral. And then A and B are just in the positive coordinate direction. So from x equals 3 to x equals 10. So when we do examples, I'll remind you of that, but that's just something to keep in mind. So that introduces our concept of voltage, our electric potential, And remember, this quantity right here is the electric. Notice the difference here. Electric potential energy. So the main thing is this word on the end, energy, makes all the difference in the world. It's just electric potential, then it's volts, and electric potential energy, then it turns out to be joules. Okay, any questions on that? So that's the quantity that we're working with. Now, what's the advantage of this? Well, the advantage of this is the exact same advantage that we got when we switched from Newton's laws of motion, where we had, the total force added up vectorially is equal to mass times d2x over dt squared, again, where dx over dt is a vector. That was a vector form of the laws of physics in some sense. And that could be used to basically put forces down that are acting on an object of mass m, and then solve for the acceleration that it's getting. And then you could integrate the acceleration to get the voltage, and then you could integrate the voltage to get the position as a function of time. That was all well and good, but it required vectors. But then we went to conservation of energy, and that represented something that we could do where we could still get the same quantities. We could still find acceleration, we could still find velocity, we could still find forces, but we got it with scalar quantity, so it made it a lot easier, at least initially. Okay, so this does the same thing with electricity. It allows us to use scalar quantities, specifically the voltage, and that's going to be much appreciated. So let me give you a rundown of exactly how cool this universe is with regards to this. So we talked about conservation of energy, and one of the reasons we use the phrase conservative or conservation is because things for which you can define a potential energy are called conservative forces, and conservative forces are conservative fields. So I'm going to call this conservative fields, and I'm talking fields like, for every x, y, z in some portion of space, you're going to assign it a quantity. Well, the very definition of a conservative field is something that's kind of crazy, but you take this neat vector calculus operator and you take a cross product of it with the electric field, and you get identically zero. Not zero if I put in certain values of x, y, and z, but zero period. Okay. Now, what is that? Well, this operator really is kind of neat all by itself, but basically you put an I hat and then you take the derivative with respect to x. So it's what we call an operator, where it needs something right here to operate on. If you put a scalar in there, then you're going to take the derivative of the scalar. If you put a vector in there, then you're going to have to either put a dot or a cross and say what kind of operation it's doing. But we write it with placeholders like this, so you can imagine whatever was to the right of it goes right here. And again, it also goes right here. And then again, whatever goes there, goes here, also goes right here. So this is partial with respect to z. So that's the operator. It's called the gradient. Nabla is what they call it in Portuguese. But for instance, in this case, you're going to actually take and calculate the determinant of a matrix whose top row is I hat, J hat, K hat. And here's a simple way of writing that. It doesn't take as much paper. Since that's the first vector in the cross product, you're going to write partial sub x, partial sub y, partial sub z. See how I didn't have to write that whole fraction? I can just put that down. Everybody knows what I'm talking about. And then this would be E sub x, E sub y, and E sub z. I do have some demonstrations of how you calculate that on my YouTube channel. You don't really need it for this course. It might be something I, get you to do as a single assignment one time, but you really don't need it for this course. I'm just giving you some deeper understanding of what we're finding. So anything for which you can find a conservation law for, it might be considered a conservative field. And then once we establish that, then you can say, well, obviously this must be true. And this quantity is called the curl. And it just means that the field has zero curl. And it literally, if you actually made an electric field for which this is zero, or a field for which this is zero, you would see it doesn't have any arrows going around in circles. Whereas something that would have arrows going around in circles for the field, that would be a very curl full field. And of course, that wouldn't be a conservative field. Now, once this is true, a whole bunch of other things become true. So one of the things that becomes true is that the integral from A to B of E dot dl is just equal to some V of B minus V of A, independent of path. So we could take that integral that I just calculated, that E dot dl, that's a line integral. And what I'm saying is if we start at A and we ended at B, we could go straight there, or we could go along the x-axis and then along the y-axis, or we could go along the y-axis and then along the x-axis, or we could do this crazy thing, and it wouldn't matter. In every answer, I'm just going to get the same quantity. And in fact, we can represent that quantity as some function at B minus some function at A. So once one of these things are true, all of them are going to be true. Here's another one. The integral over a closed path of E dot dl is equal to 0. I think it's pretty obvious that this is the case. What they're saying is if you go from, say, A and do any kind of crazy stuff, and end up back at A, then you're going to get 0. And that should make sense because V of B minus V of B is going to be 0. Now, in addition to that, there's another thing, and it basically says, let me show you some mathematical symbols. Upside down E means there exists a scalar function V that means such that E is equal to the negative gradient of V. So there's that operator again. Okay. If this acts on as a scalar, then basically you're going to take the derivative of the scalar with respect to X, pretending all the other variables are constant, and slap an I hat next to it. Then you're going to take and add that to a derivative with respect to Y, slap a J hat on it. Then you're going to take and add those two to take the derivative of it with respect to D and slap a K hat on it. And lo and behold, you're going to get back that electric field that you had originally. Okay. And of course, this one means that that first one's true as well. So they're all this cyclic thing. So that's the bigger, deeper meaning of vector calculus and what we get. But it's kind of nice once you have that, then you know there exists a scalar field. So for instance, the fact that we had U gravity equals mgh, that told us specifically that the gravitational force has no curl. So if you calculated the curl of Newton's law of gravity, you get 0. It tells us that if you integrated mgh or mg.dl over any path from A to B, it'd be independent of the path, and it'd just be basically U of B minus U of A. And if you did a closed integral, this is what we learned before too, right? If you throw a ball up and then it comes back down, it'll be going the same speed as it had before. That's what that says. And then ultimately, this is that scalar potential. In this case, it was U. In this case, it's V. Okay, so it's something we've already learned about before. And you probably noticed, in fact, that if you say that U of X, Y, Z is equal to mg, and instead of using h, let's use y, because y is often used as our upward coordinate. This is only a function of y now. So if I take the gradient of U of X, Y, Z, Notice the derivative of it with respect to x is 0. The derivative of it with respect to z is 0. And I get basically the derivative of it with respect to y is just mg. So that the negative gradient of u is equal to negative mg j hat, which is exactly the way we picture the gravitational force. It's the weight of the object, mg, and it points down. So, wow, that's amazing. It's exactly right, right? So that's the aerial view of what we're learning. Now what we want to do is we'd like to work some specific examples to help us make sense of this new quantity, the voltage. So I'm going to look, I had written this up and now I seemingly can't find it. So that's awesome. Ah, here it is. Maybe. Yes. Okay, so let's consider, for instance, I think I actually have a problem for this. Let me find this real quick. I'm going to go back to my webcam for a second. I'm going to go into a file folder and see if I can actually find. I actually wrote up some problems for this. No, it's on my other computer. Never mind. I will scrap that. I will go back to my document cam. Whoa, wrong one. Erasing. Excuse me. All right, so let's consider an example. Let's consider, for instance, an example where we try to consider what happens when we move, say, a charge from one plate of what we call a capacitor to another plate. Okay, so what I'm going to do is I'm going to imagine that last Gauss's law problem we did was basically a infinitely large flat plate that had a charge distributed over it somewhat uniformly. So now if we take two of those, say this one has a bunch of positive charges on it, distributed uniformly, and this one has a bunch of negative charges on it, distributed uniformly. The charge per unit area being sigma. Then what we learned from Gauss's law is that the electric field from the positive plate, at least to the right, so I'm going to draw a coordinate system right here, and I'm going to say that's my x-axis. So for the positive plate, ignoring the negative plate, it's going to be sigma over 2 epsilon naught I hat for x greater than 0, and negative sigma over 2 epsilon naught I hat for x less than 0. That should make sense, right? If I'm on this side of a positive plate, it's going to push positive charges this way. And if I'm on this side of a positive plate, it's going to push them this way. So that's what that's saying. Now, the electric field for the negative one, if I call this position right here L, then E negative is basically, again, a piecewise function. It's if a positive charge is over here to the left, it's going to be attractive to it. So it'll be a positive sigma over 2 epsilon naught I hat for x less than L. And then it's a negative sigma over 2 epsilon naught I hat for x greater than L. Okay. So now if I look at the three regions, over this side, I've got a positive plate that's causing E positive point this way. And of course, E negative points that way. And you can see the net effect is E is equal to 0 out here. Similarly, if I look on this far right side, what I see is E positive is pointing this way, and E negative is pointing this way. So E is equal to 0 out here. But in between, something really cool happens. E positive points that way, and E negative also points that way. So you get E is equal to sigma over epsilon naught I hat in between them. Does that make sense to everybody? Now, the way it's supposed to work out is this plate obviously is not infinitely large, but the distance between them is so small compared to how big they are, it might as well be infinitely large. So these equations are pretty accurate, at least away from the edges. Okay. So that's what we call a parallel plate capacitor. We'll learn about that in the next chapter, but right now we're going to use it to create, because this electric field does not depend on distance at all. It's just sigma, the charge per unit area, over epsilon naught, and when a number 2 in there or whatever, or in this case without the number 2, that means the uniform electric field. So it's a really simple case to study. So what we can do is we can say, suppose a negative charge, such as an electron, is placed near the negative plate in a parallel plate capacitor. If the electron is free to move, will its electric potential increase or decrease, and how will the electric potential change? So if we put a negative charge right near the negative plate, so what I'm going to do is look at the negative plate, zoom in from the side, and put the electron right here. Okay. The electron, being that it's negatively charged and this plate is negatively charged, they don't like being next to each other, do they? So because of that, this electron of its own is going to move away. Okay. Now what that means is that the actual particle is going to move on its own, and in fact right now its potential energy is quite high. So U is high here, but U will be low here, right? And that the reason why is you can think of it as we are attracted to Earth due to gravity. So if we're on top of a telephone pole, then this is our high potential energy. And then when we fall down and land on, say, a tabletop instead of the ground, that's a low potential energy. Even if it's not zero, it's low, right? We're closer to the thing that we'd like to be close to. By the negative electron moving from the negative plate closer to the positive plate, we've actually got it more close to the thing it's comfortable with. So what we found is delta U, which is final minus initial. So that would be U low minus U high. That's the final minus initial. You can see that's actually going to be less than 0. But the change in electric potential, delta V, which would be V, I'm just going to say this is B, by the way. So let's call this position B and let's call this position A. So this will be VB minus VA. That's going to be delta U over the charge. And of course, delta U is negative, or we'll just leave it as delta U right now. And I'll put that over negative E. Now that quantity we just showed was negative. And this quantity, of course, is negative. So delta V is greater than 0. So that's a big thing to understand about this voltage. Voltage is like a potential energy, but it's not exactly a potential energy. Potential energy always goes down when the object becomes more, quote unquote, comfortable with respect to the force that causes that potential. So it's perfectly natural for an electron to go from a negatively charged plate towards a positively charged plate. And that would be, in fact, a decrease in potential energy. But voltage in that case is actually an increase. So negative particles actually move in a way that their voltage increases. Positive particles, on the other hand, they move in such a way that their potential energy and their voltage decrease. So that's sort of the big rule we're getting out of this, is negative particles go to increasing change in voltage, but decreasing potential energy, whereas positive particles go to both decreasing potential energy and decreasing voltage. So that's something to keep in mind as we progress, because that's a concept that'll help you. Now, the good news and the bad news is that generally speaking, we pretend when we're working with circuits, we pretend as if net positive charges are moving around the circuit. So if we had a battery, let's say, if we had, for instance, a battery, and here's the symbol that we use for a battery, you might use just that, a long bar with a short bar. A lot of times you'll see people use 2, or occasionally you'll even see people use 3. But the main thing is the long end is the positive voltage and the short end is the negative voltage. And it might be connected to, say, a light bulb, which we just recognize as a load. And any load is essentially a resistance, which we do by that little squiggly line here, which sort of like looks like the filament in a incandescent light bulb. So that's why that's sort of fitting. So what we know is, or what we pretend is, that there's little positive charges flowing around here like this. And that's called conventional current. And as I told you, Ben Franklin had a 50-50 chance, and he thought the ones that we knew of as positive were the ones that were going around here. It turned out to be exactly wrong. It turns out it's actually the ones that we think of as negative are going the other way. But luckily, unless you're doing something called the Hall effect experiment, you really can't tell what is happening. So you can always pretend like positive charges are moving the other way, and that's just fine. Okay, so the Hall effect is pretty much the only thing you can do, the only experiment you can do to detect whether it's negative charges going one way versus positive charges going the other way. And basically what that is you run a current through a wire in a magnetic field and an electric field, and you see whether this side becomes positive and this side negative, or this side becomes negative and that side positive. And you work out the physics of it, and it tells you whether it's negative charges or positive charges. So that's how we're going to do that. Now let's look at another example. Let's take a capacitor now that I've shown you what a battery looks like. For instance, I'm going to take and connect a battery to a capacitor. And obviously this is going to be the positive side because it's connected to the long side of the battery. By the way, on a AA or AAA battery, or a C battery or D battery, this is the side with the little nipple on top. So that part that goes up like this, that's the positive side. And this down here is the negative side, just in case you ever need to know. So we're going to connect that to the positive side, and that's going to be 50.0 volts. And then here's the capacitor is going to come back here to this, and this is going to be 0.0 volts. Now, in principle, you can actually call 0 volts anywhere on the circuit, and all you have to do to make it true is connect that particular part of the circuit to a ground, which I've mentioned before is literally just a steel rod coated in copper that goes down about 8 feet into the ground. Okay, so if you connect any part of this circuit to a wire that's connected to that, then that will automatically be 0 volts. Usually we say it's right here, but we pretend the wire has no resistance. So this whole thing from basically here all the way here is 0 volts. And then from here, which is a 50-volt battery, all the way to here is a 50 volts as well, because again, though there might be some current flowing around here, we don't expect the potential energy or the electric potential to decrease significantly because the resistance of the wire is so much less than all the other stuff in the circuit. So we're going to have this circuit right here, and what I want to do is find out what is the actual what is the electric field in going from the left side to the right side. So I want to find out what E is. Okay. So what we know is the electric field inside is in fact uniform, and we're going to get an expression for the electric field in terms of things like voltage and the geometry of this particular device, which is that the plates are separated by a distance d. Can everybody see that's the distance d? I just realized how small I wrote it, and I don't know why I did it. But anyways, the separation between these two plates is d like meters, and the voltage difference between them is delta V, which is 50 volts minus 0 volts. So what I'm going to do is I'm going to say VB minus VA, and I'm basically going from A to B, is equal to the negative integral from A to B of whatever this constant electric field is, which I'm just going to call E in the I hat direction, okay, dotted with DL, which I'm just going to call DX I hat. So I automatically just chose to put the DL in this line integral. I put that in the positive coordinate direction, okay? Well, I'm going to say my positive coordinate direction is actually this way as well. So that means I'm going to have to integrate it. Since I put it that way, I'm going to have to integrate in the direction I'm going, which happens to be from A to B anyways. Okay. So that all works out. And that's why most of the time there's no problems with you not knowing it's a line integral, because most of the time it's positive and positive. So you wouldn't get it wrong anyways. So now what I'll get is negative, and this is supposed to just be an E. I don't know why I put a vector symbol over top of it. That's just plain a constant E. Okay. And since it's a constant, I can go ahead and write from x equals 0 to D. And I'm going to write E dx times I hat dot I hat. And that I hat dot I hat, as we've seen 1,000 times before, is just 1. And in fact, the E can come out, which is why I started off by saying it's positive. So I'm going to say negative E times the integral dx from 0 to D. And when I get that, I'm going to get negative E times D. Okay. So what we see is delta V, which, as I said, was VB minus VA, was equal to negative E times D. And this gives us a whole new unit that we can use for the electric field. If I just talk in terms of magnitudes, then E is equal to delta V divided by D. So this is magnitudes. Now, you did expect it to be negative like we got, because I went from high voltage to low voltage, and clearly high voltage to low voltage should give you a delta V is negative. But what this tells us is this neat thing that the electric field, which had units of 1 Newton per Coulomb, for instance, is also equal to 1 volt per meter. So now we can stop using the newtons per Coulomb whenever it seems more reasonable to use volts per meter. And if we're dealing with a parallel plate capacitor, we know how the voltage is going to change. It's going to start off at V, and then each meter it goes over, it's going to drop in the electric field by an amount of by an amount of the total voltage divided by 1 meter. So that's a whole nother neat new thing that we got from using this electric potential stuff. So that's kind of nice. Anybody have any questions on that? All right, so now that's sort of an example, but there's also a teaching example in that I just used it specifically so you could see that the electric field has a new unit that we can use and see how it's related to the normal characteristics of a capacitor, which is what's the voltage on it, how far away or how far apart of the plates, and that sort of thing. So that had multiple uses, but it was sort of an example as well. Now what I'm going to do is see that we can actually use something like Coulomb's law to calculate the voltage. So what I'm going to do is I'm going to imagine a 3-dimensional coordinate system, and I'm going to imagine it like in spherical coordinates, like I told you guys before that it would be helpful for you to have some sense of. But again, I'm not really requiring you to know that much. It just helps me with using symbols that are nice. So what I'm going to do is I'm going to imagine a charge, total charge Q, at or on this sphere of radius big R. So that's the electric charge. It's a finite sphere, and since it's nice and spherical, and the charge seems to be spherically along the surface, let's say, then from that we should be able to realize it's going to act just like a point charge. But what I want to do is I want to calculate basically the change in voltage and going from somewhere where the voltage should be 0 up to some position R away. So you can imagine in spherical coordinates, the coordinates spherical coordinates are given R, theta, phi. That's the 3 variables, where R is just a distance from the origin. So you might imagine, for instance, R might be this distance right here, and this might be the point P that we're dealing with. Now, what that means is you can drop a vertical, and that will give you in the XY plane an angle theta separated from the positive x-axis in the counterclockwise direction, and then an angle phi down from the z-axis called the polar angle. That's really what the coordinates are, but all I care about is using this R. Okay, so I'm just giving you that as a little bit of a heads up on what the spherical coordinate system is. And what I'm going to do is I'm going to imagine the change in voltage delta V and taking it from E equals 0 to R that I show here. Okay. And at E equals 0, we expect V to equal 0. So what I'm going to do is I'm going to say, well, what I know is for a spherical charge distribution, the electric field E caused by it is actually equal to the charge Q over 4 pi epsilon naught times R squared in the R hat direction, right? If Q is negative, of course, then that negative is going to multiply by this and make it point towards this coordinate origin. And if it's positive, it's going to point away, which is exactly what we expect the electric field to do. Does that make sense to everyone? So that's our electric field.
Say that one more time.
Okay, so it points in the radial direction. Now, radial direction just means you take a line from the origin to the point that you're at, and you just continue it that way, 1 unit, and then that's the R hat vector. So if Q happens to be negative, then that negative is going to multiply by this R hat, and you're going to see the electric field pointing towards the origin, which is what you'd expect if this charge was negative. You'd expect the positive charges to be drawn towards it. Whereas if it's positive, then you'd expect it to be pushed away from it, and that works in both cases. Does that make sense?
Yeah, thank you.
No problem. And now you can also see that as R, if you take the limit as R approaches infinity of E, you get 0, right? So what we're going to do is we're going to calculate the voltage delta V, and that's going to be V final minus V initial, which is a negative integral of E dot dl. And of course, we're going to take it from infinity to R. Then, since we're going from infinity, that's going to be equal to 0. And in fact, what you'll get is the electric potential at that point right there. So I can say this is negative integral of Q over 4 pi epsilon naught R squared. That's going to point in the R hat direction. Now, I have evidently chosen to take the range of integration as dictating which direction I go. So I'll say infinity to R. That means I have no choice but to just choose the positive coordinate direction for my DL. So my DL is just going to be dr R hat. Whereas I'm actually going in the negative r hat direction. But that was already established by this going from infinity to r. I could have did r to infinity, but then I have to put the negative dr r hat. Either way is acceptable. Just you got to do it once and exactly once, or you'll be off by a sign. So now I can see the q, the negative, and the 4 pi epsilon naught all come out in front, and I get the integral of dr over r squared r hat dot r hat, which I think by now you all recognize that any r hat dot r hat is always going to be 1, and this is going to be from infinity to r. Well, the integral of r to the negative 2 is negative 1 over r to the negative, or excuse me, negative r to the negative 1. So that's going to become positive q over 4 pi epsilon naught. And now I have to do 1 over r. The negative was already taken into account by putting that positive there. But now I got to do this guy. So that'd be 1 over r minus the limit as r approaches infinity of 1 over r, which everybody knows the limit of 1 over r as r approaches infinity is 0. So lo and behold, I have a formula for a spherical distribution of charge a distance r away. The electric potential is q over 4 pi epsilon naught r, and that's a scalar quantity. So those problems we did earlier where we have like a charge here and a charge here and a charge here and a charge here, and they might want you to calculate the electric field dead center. That was a pain because, you know, this one had a vector and had an x component and a y component. This one had an x and y component. This one had an x and y component. This one had an x and y component. You had to break all those up. Then you had to add them with the right coordinates added to the right coordinates, you know, x's to the x's and the y's to the y's. And then you had to compute what the net vector was by putting the x component and the y component in space and then find the angle. All that was a nightmare. Now all you got to do is just add them as positive and negative numbers, because voltages can be negative, right? You could have a negative charge, but you just add them as scalars and it's a lot easier. So this is another important formula that we can use. Now, we could also calculate what the voltage is at any point within this. If we assume, for instance, that let's say that the charge was on the surface of a conducting sphere. So in other words, if we pretend the sphere, assume the sphere is a conductor. This is sort of what you learned, hopefully, from the reading of the chapter on Gauss's law. If this sphere were in fact a conductor, conductors are materials that particles of charge are free to move around in it. That's what makes them useful, because those charged particles, the electrons, for instance, can move around and take heat from one part of a bar and deliver it to another part of a bar, and the heat being just the average kinetic energy of the electrons. But it can also do it with electric fields, causing the charges to move from the positive end to the negative end if they're positive particles, so on and so forth. So that's really what a conductor is. Therefore, if you put a charge Q on this conductor, all those charges are free to move. They're going to maximize their distance away from each other because they're all going to be the same sign. That means they're all going to appear all the way out at the outside edge. Okay. And in fact, if you use Gauss's law, you could come up with the electric field inside and out. And basically what you'd find is that the electric field goes to 0 inside. And that's what I'm going to show now. So what I'll do here is I'm going to use Gauss's law again. And I'm going to take my sphere and say it's that. And let's say it has a radius r. And I'm going to calculate basically the electric field for, we already know what the electric field for r greater than r is, but I'm going to do that anyways. So let's first take r greater than big R. And what I do is I imagine a concentric Gaussian sphere. that's concentric with the same sphere. It has, of course, a radius little r. And then I make the hypothesis that E of r theta phi is just equal to E of r, and it points in the r hat direction. And then I'm going to say dA, the little surface area element, because remember Gauss's law is the closed integral of E dot dA is equal to Q enclosed over epsilon naught. I'm going to say the dA, even though I could work it out for spherical coordinates, it could be r sine phi d phi times r d theta. That would actually be what it is. That would be the surface area of it. All we're really going to call it is dA times r hat. Okay, so we're imagining this little patch on here, if you will, like a tire patch on a basketball, say. That's the little differential area element. It's going to also point radially outward because it's perpendicular to the surface. And because we're on a surface of constant radius, E of r is just a constant number. So the left-hand side of Gauss's law, the closed integral E dot dA, is just going to become the integral of E of r hat dot dA r hat, which is just E of r times the integral of dA r hat dot r hat, which is just going to be E of r times 4 pi r, lowercase r is what I meant, and 4 pi r squared, because that's the surface area of the sphere. The right-hand side of Gauss's law, on the other hand, is Q enclosed over epsilon naught. Well, the Q enclosed is just a Q, so that's just Q over epsilon naught. So I say LHS equals RHS, and I get E of r times 4 pi r squared is equal to Q over epsilon naught. RE is equal to Q over 4 pi epsilon naught r squared r hat. So that's our electric field. That's exactly the electric field that I used here. So I now know why I could use that electric field to find that voltage outside, right? But in order to find the voltage for R less than R, which I could do on here, I need to know the electric field inside as well. So for R less than big R, when we go to do that, now I have to draw another Gaussian surface. I'm going to draw this one in blue. That radius is R again. And I'm going to make a hypothesis that E of r theta phi is actually just going to be E of r hat. I'm going to say that this is not related to the hypothesis, by the way, that dA is going to equal dA r hat, and the left-hand side is going to be the integral of E dot dA, which equals, of course, E of r times 4 pi r squared. The problem is, because this is a conductor, the right-hand side, which is Q enclosed over epsilon naught, if any charge is inside of this, it's closer to the other charges than it would be if it were on the outside. Therefore, all the charges inside must be 0. So 0, that means E equals 0 for R less than or equal to big R. And actually, I shouldn't put that equals. I'll just say less than big R. Okay. So that's the other part. E is equal to 0 for R less than big R. And now I can use V is equal to the negative integral from infinity to R less than big R of E dot dl to calculate the voltage inside. Okay. So what I know is this is going to be the negative integral from infinity to big R of Q over 4 pi epsilon naught R squared R hat dot dr R hat. Sorry about that. I put my hat in the wrong place. Okay. Plus, or actually I should say minus. Let me fix this too. That aggravates me already. This is dr R hat minus the integral from R to little r of 0 dot dr R hat. Okay. This part I think is pretty obvious. Notice the only difference is I'm changing that R to big R. So I should replace that. And now I get minus 0 when I do this part. So it just becomes Q over 4 pi epsilon naught big R. And in fact, if I made a plot, I'm going to go up here to make a plot of both E. If I made a plot of E of R, then what I'd get is that the electric field was 0 out to big R, and then it became Q over 4 pi epsilon naught R squared, right there. And then here, it fell off as 1 over R squared. So that's what the electric field would be as a graph of a function of position. But the voltage, on the other hand, and I'll use a different color for that one. I'd go out here to R, and I'd say this is Q over 4 pi epsilon naught R, excuse me, big R. And in fact, this would be a constant because notice the electric field was this constant for R less than big R. So it's going to be that constant. And then it would fall off over here like 1 over R. You can see a discontinuity in the electric field equal to sigma over epsilon naught because notice sigma over 4 pi R squared is, excuse me, Q over 4 pi R squared is sigma. So that's exactly what we found earlier, that you will have a discontinuity whenever there's a surface charge, and that discontinuity will be equal to the charge per unit area divided by epsilon naught. Any questions on that one? Okay. 445, let's just go to 610, 610, yeah. All right, so that was sort of two examples all meshed into one, but it was giving me another chance to use Gauss's law because, like I said, we do Gauss's law in one chapter. We're going to do it a lot more in chapter 24, for instance, okay? But I wanted to keep doing it so you can see that, yeah, we only spent one day on Gauss's law chapter, but we're actually spending many more days on that. So you are really in a good position now to take the chapter 21 and 22 tests. So we've got that. Those are some very good results. There's stuff that we'll use over and over again, but we can now also use the fact that the voltage due to a point charge is just that Q over 4 pi epsilon naught R, and we can do stuff that used to be really, really ugly and hard, and we can do it really, really easily now. So for instance, let's do a dipole. I'm going to put up some of these extra pins I have down here. What I'm going to do is I'm going to imagine an X and Y axis. And I'm going to come out here to a distance of 1.7 meters. I'm going to put a charge Q2 equals positive 0.111 microcoulomb. I'm going to put a charge Q1 here is equal to negative 0.111 microcoulombs. And then I'm going to go up here, call this position 2 meters. I'm going to put a charge Q3 that happens to be right over 0.85 meters. I'm going to put a charge Q3, which is equal to 0.111 microcoulombs. Okay. And let's see. Okay. And I'm also going to imagine a point right here at 0.75, but right there, that's the point P. Okay. Now this would be a nightmare if we actually had to calculate the electric field at point P. It's not that much of a nightmare. Calculating that would be a pain. But I'm going to ask for the voltage at P. And that's going to be easy peasy. Okay. So what I do is if I want to know the voltage at P, that's just equal to the voltage at P due to 1 plus the voltage at P due to 2 plus the voltage at P due to 3. And notice these don't have vector symbols over them. That's what makes it nice and neat. So the voltage at P due to 1 is just due to this little charge here and that little distance there. So all I got to do is I got to write negative 0.111 times 10 to the negative 6 coulombs over 4 pi 8.85 times 10 to the negative 12th. Now that's Coulomb squared per Newton meter squared is what it used to be. But we now learned, notice the units of epsilon, I'm going to put up here, is equal to Coulomb squared per Newton meter squared. But notice that we learned the Newton per Coulomb is the same thing as a volt per meter. So I could say a Coulomb over, let's say the Newton per Coulomb would be down here. And then the meter squared would be right here. Now, if I actually did this math, what I'd see is the N would end up down here like I want it, and the C would end up right there like I want it. So that's now going to be changed to volts per meter. So I'm going to say coulombs, meters, volts, meters squared. That meter squared is going to cancel out with that. So now the unit of this is just a Coulomb per voltmeter. So that's the new unit for this. That makes life a little easier for us. So I'll go ahead and change it now. You can look at that as a sidebar if you like. So I'm going to write that as coulombs per voltmeter as the units of the permittivity of free space. So that's 4 pi epsilon naught. And now I just need the distance. Well, the distance from here to P is obviously 0.85 squared plus 0.75 squared. Just by the Pythagorean theorem. And now you can see this Coulomb is going to cancel out with this Coulomb. This one's going to give us a meter. That's going to cancel out with that. And that's going to give me just a volt. So the volt in the bottom is going to come to the volt at the top. By doing my extensive work on this rough mathematics, I found that this voltage was negative 880.47 volts. And that's 3 extra sig figs. Now you might think, well, that's nice, but and you should calculate that and make sure I didn't make a mistake. You might think that's great, but it's really even more great because the symmetries here, the way I made everything up, life is a lot easier to calculate now. So now that I can do, now that I've done V at P due to charge 1, I can do V at P due to charge 2, and you see the only difference should be a sign, because this 0.85 is half of 1.7, and it's the same distance away. So everything's exactly the same there. So I'm going to say V at P due to 2 is equal to, in this case, positive 0.111 times 10 to the negative 6 coulombs over 4 pi times 8.85 times 10 to the negative 12th. We discovered that was coulombs per voltmeter. And then that distance, of course, would be, again, 0.85 meters squared plus 0.75 meters squared, square root of all that junk. That gives me the exact same number, but with the opposite sign. So that's going to be 880.47 volts. And now all we have is the voltage at P due to 3. So the voltage at P due to 3 should be equal to, notice the charge is 0.111, so 0.111 times 10 to the negative 6 coulombs over 4 pi 8.85 times 10 to the negative 12th coulombs per voltmeter. Now in this case, the distance is really easy because this is 0.75, but that's 2 meters up, so that's just 1.25 meters. So this one's just 1.25 meters. So yeah, I had to calculate it again, but at least it's something where I don't have to do a square root. When I get this, it's 798.47 volts. So when I add these three, the voltage at P just turns out to be this plus this plus this, no vectors. So that cancels out with that. I just get 798 volts. That's easy peasy, right? All right. So it's 5:59 now, so that's not too bad. Anybody have any other questions? Have any questions on any of that? Nada?
No.
Okay. Did somebody say you had one?
I just had a question on regards to the previous lecture. I missed it by mistake, and just want to know which video it was. But that could be after class.
Yeah, no problem. Yeah, it's actually is up. I put caught up with all of them. I also put up the old ones that had been forgotten. So that's all been put up now. And when you're looking for it, what you're looking for is, I think I can write it on this page. Be pretty good. Let's see what this is. Yeah, this is a page from this lecture, I think. All you're looking for the last lecture is you're looking for a video that has PHY242N05B. There will usually be a space in here, so the file name will have that in it, but the actual, in the description on the YouTube, it'll just say 011922. So that's the date. That's the section number. By the way, don't feel obligated to just look at your own section number. Sometimes we do some other examples in other sections, so you're welcome to look at those too. So anything you see with a PHY 242 is something that may be helpful to you. But if you're looking for your lecture, you got to look for the date that you missed as well as that.
Okay, thank you.
Okay. No problem. All right. So the last thing I wanted to show you with regards to this chapter, or excuse me, with regards to this material today, is I wanted to show you how we could use that information that I told you, that if a field is conservative, that means the curl is equal to 0, and that means the line integral is independent of the path, and that means the closed integral is 0, And then that last part, it means that there exists a scalar field such that the negative gradient of that scalar field is in fact equal to the electric field. So that's the next thing I want to do, is show you one like that. And the way I want to do it is I want to take a result that was gotten by that nasty calculus method. I'm really getting dangerous here with this, by using those intervals. So if you remember in chapter 21, we did an infinite plane, but we started off by doing a little ring of charge. So you could do a little ring of charge like this, and might as well do it now. So I think I will. So I'm going to do an XYZ coordinate system, X, Y. And now what I'm going to do is I'm going to draw a ring of charge. It's supposed to be really, really thin, but it is a ring of charge, okay? And it has a uniform charge density lambda and a total charge Q, and it has a radius, say, big R. And what I would like to do is find the electric field some distance Z above it. So what I've put together for you is a way of writing out Coulomb's law in vector form. So that what method is dE is equal to Q, or dQ, I should say, over 4 pi epsilon naught. And then I say RP minus R dQ, magnitude of that cubed, and then times RP minus R dQ, right? So what I'm going to do is I'm going to come over here and I'm going to imagine that I go out an angle theta, and then I let that angle theta increase by an amount d theta. Okay, so that's that little distance, is that right there. Then this little bit right here is going to be my dq, and which is the same thing as d big Q. That's going to be lambda times the radius, which is r, times d theta. Okay, and that's just from the old trigonometric equation, S equals r times theta, you know, the definition of radians basically. So the length here is just r times the angle, which is d theta. And then if I multiply the length times the charge per unit length, then I get the differential charge. And by the way, it should be obvious that lambda is equal to Q over 2 pi r. Everybody agree with that? Now, here's the weird part. The RP, that's the vector that points from the origin to P. Well, that's just Z K hat, easy peasy. Well, the other one, if at least if I stay in cylindrical coordinates, looks kind of odd. So I'll say RQ, or R sub DQ, is just R times R hat. But the problem is R hat is actually a function of theta and phi. So this is a big rule for you guys when you do start using these special coordinate systems, cylindrical. Actually, this is theta. Actually, this one's just theta, if I remember correctly. Yeah. When you start using these special coordinate systems, cylindrical, spherical, hyperbolic, whatever, you'll have unit vectors just like you have I hat, J hat, and K hat. But those unit vectors are actually functions. So when you actually integrate or differentiate them, you actually have to take the derivative or the integral of them and stuff like that. Whereas if you reduce it all to I's, J's, and K's, they're just constant. So they always come out in front. So let me zoom in a second and show you what this is supposed to look like. If I look at the x-axis and the y-axis, and I come out here to some point P, so we're ignoring the z component. So cylindrical coordinates just has r theta cylindrical, just has r, and sometimes people will use like rho for that because it's different from the r in spherical coordinates, or sometimes they'll use rho for the spherical coordinates. they'll have rho, r, theta, and then z. So the z is the normal coordinate, but they just use polar coordinates for down here. So this distance from here to here is just r. This angle's theta. And then they imagine a unit vector that sticks out this way is r hat. And then they imagine 90 degrees ahead of it is a unit vector theta hat. Okay. So it's helpful to know these things. Now, if I project the XY axis on here, then I can see this is the angle theta. And I see that r hat is just going to be the length of this guy, which is 1 times the cosine theta. So I just get cosine theta I hat. And then this one is the y component. So that just should be the length of this one, which is 1 times the sine theta. So that'd be plus sine theta j hat. So that's what r as a function of theta is. And I think you can even tell from this diagram, I'll do it. We don't need it now, but it's kind of nice to have. The x component is going to be negative sine theta. And then the y component is just going to be cosine theta j hat, which you might notice that dr hat over d theta is equal to theta hat. So those are some actual facts that come in handy, but I can actually use this now instead of, I don't want to integrate an r hat because that means I got to integrate with the thetas and all that stuff. So I just put it back in terms of i's and j's. I still have to do the integral, but at least it takes care of it. So now I can write r dq as in fact equal to r cosine theta I hat plus r sine theta j hat. Now all I have to calculate is rp minus r dq, which I think you can tell rp is that. So that's going to be z k hat minus r cosine theta I hat minus r sine theta j hat. And that might look a little scary to you, but it's really not that bad. For instance, when you go to calculate the magnitude of this rp minus r dq, it might help rather than think of all this mess that realize it's just the distance from here to there. From this spot right here on the ring to that spot right there. Well, you know that distance is z, and you know this distance right here is r. So you can just say, obviously, this is going to be the square root of r squared plus z squared. And life just got a lot easier. So now I can continue. I can do E is equal to the integral of dE, which is going to be equal to, I'm going to take all this extraneous crap out in front, like I'm going to take the lambda, the r, the 4 pi epsilon naught, lambda r, I think the r is up there, yeah, r d theta, over 4 pi epsilon naught. That's all out front. Now I have the integral. What's left of the dq is just a d theta, so I'll put the d theta here. And now I'll do z k hat minus r cosine theta I hat minus r sine theta j hat. All that is a vector that is to be integrated, even though it's to the right of the d theta. And then all that is going to be divided by, I've already taken the 4 pi epsilon naught out front, but I got to take this square root and cube it. So it's going to be r squared plus z squared to the 3/2 power. But guess what? We're integrating with respect to theta. All that junk is zero. I mean, all that junk is constant, excuse me. The other thing I was going to say, and that's why I jumped the gun and said zero. If you look at the symmetry of this, for this angle theta, you're going to have an electric field that points that way along this line connecting this point and this point. Is going to have a I hat component and a j hat component and a k hat component. Now, if I go 180 degrees to the other side, I'm going to have exactly the opposite I hat and j hat components. So they're going to cancel out. So the symmetry of this tells us that these two components right here are going to completely cancel out. And I think you can see that because we're going to integrate over theta equals 2 pi. And of course, cosine, which looks like that, is clearly going to integrate to 0. And sine, which looks like that, is clearly going to integrate to 0. So that's really what's going to happen. The only thing that's going to survive is this. You can carry out all the stuff you want to, you just don't have to. So I'm going to write lambda r over 4 pi epsilon naught z squared plus r squared to the 3 halves. Okay, that's my actual all of this plus z k hat is all that. Now I have left the integral d theta from theta equals 0 to 2 pi. I think you can see what happens now. The integral of d theta from theta equals 0 to 2 pi is just 2 pi. So the 2 pi times r is just the length of the loop, and the 2 pi r times the lambda is just the q. So I'm going to get q z over 4 pi epsilon naught z squared plus r squared to the 3 halves, all that in the k hat direction, and that is our electric field right there. Any questions on that? So that's one of those problems from like chapter 21. But guess what? Now that we've seen it this way, we can do a very easy version of that for the voltage using dV equals dq over 4 pi epsilon naught r. You can now integrate that with this and you'll get a voltage. And then if you take the negative partial of V with respect to Z, you'll get exactly that expression. Okay, we ran out of time, but you can do that if you'd like. I'm probably going to do it after you guys leave. I'll do it on here, and that way it'll be on the video, so y'all can still check it out. Let me go ahead and open the floor to questions. Everybody, of course, is free to go. We ran about 4 minutes late. Y'all are free to go, but if you have any questions, stick around. I'll wait for the last of you to leave. Paul or Shimon, do you have any questions?
I'm good. Sorry, my app was just being finicky.
No problem. Was the images any better today?
Yeah, the images seem fine.
Okay, cool. Well, I'm gonna go ahead and finish this problem. If you don't have a question, Paul, do you have a question either? Are you even there?
Thank you.
You're welcome, Shimon. All right, so let's do this. Now I'm going to attempt, I did not practice this a priori. I did it last minute because I forgot this class was behind. So let's see if we can do it now. I'm going to again take that ring of charge, the little DQ element. This DQ is going to be lambda times r d theta. And then V is equal to the integral of dV, which equals the integral of lambda r d theta over 4 pi epsilon naught. The r, of course, is going to be square root z squared plus r squared. And I'm going to integrate this from theta equals 0 to 2 pi. So I end up getting lambda times 2 pi r. Excuse me, that the theta is no longer there because that's where the 2 pi came from, over 4 pi epsilon naught square root z squared plus r squared. Now that I have that, I'm going to say V is equal to Q. Yeah, because 2 pi r is all that's left there. So it's going to be Q over 4 pi epsilon naught square root z squared plus r squared. That's what our voltage is. Now E is supposed to be the negative gradient of V, and since there's only a z in here, that means negative k hat partial of V with respect to z. So I'm going to take the derivative of this with respect to z. So the derivative, partial derivative of v with respect to z is equal to q over 4 pi epsilon naught times d. It's actually, you can might as well make it a regular derivative now since there's only one variable. Well, I guess the r, you can still pretend that's a variable. So I'll say the partial with respect to z of z squared plus r squared to the negative 1/2 power is equal to q over 4 pi epsilon naught times the derivative of this would be negative 1/2 minus 1, which would be negative 3/2. But it's times negative 1/2. So negative 1/2 times z squared plus r squared to the negative 3/2 now. And then the derivative of this with respect to z is just 2z. So using my chain rules, this 2 and this 2 is going to cancel out. The chain rule gave me the negative 1/2 and the positive 2z. So now I'm going to get negative qz over 4 pi epsilon naught z squared plus r squared to the 3/2. Therefore, our electric field, which is supposed to be the negative gradient, is going to be negative of this, which gives it a positive. So E should equal positive QZ over 4 pi epsilon naught Z squared plus R squared to the 3/2, all that times K hat, which is QZ over 4 pi epsilon naught Z squared plus R squared to K hat. So you can see it's exactly the same expression we got by doing it the integral of Coulomb's law way. So that's it. That's just showing you full circle how we can do all that. Thank you, everyone. Have a good day.